Hello everybody. In this third lecture, where we still continue to learn to develop models, we will learn a very special class of systems. Of course, this will not be a major part of the course starting from week 2, but it's good to know models. So far we have seen linear models, we have seen non-linear models, we have seen how linear models can be used to analyze network systems, for example, the wireless sensor networks. We also saw examples about hybrid systems where you have continuous dynamics which are also governed by certain discrete events which happen. Okay, so this class of systems are called infinite dimensional systems or infinite dimensional models. A more engineering term for this is also called as distributed parameter models. So far what we saw is that if I take a resistor, it's just a little element, what I call as a lump, that it's just a small element which doesn't depend on any other parameter. Okay, so what I mean by this distributed parameter models. So we will start from examples which we know from, say, electromagnetics text. Okay, so if we remember models of transmission line, well, it's okay even if we don't remember. We had several models, right? We had something called the T model approximation, which was something like this. Okay, I just ignore the dissipative elements here. We also had something called the pi model, right, which was maybe something like this, where the entire capacitance was clubbed into just one single capacitor. The inductors were distributed into two, L by 2 this side, L by 2 that side. Similarly, if I have what I call as a pi model, I have the entire inductance of the transmission line lumped into just a single inductor, and capacitors just C by 2, like into two different elements. Okay, so a simpler version of this is also the L model which we consider here, right. So I just have R, L, G and Z. Okay, what is the difference between having this model and what actually happens is that the resistance is distributed over the entire length of the transmission line. Say if I take, say if it's a 5 meter line, the resistance from 0 to 2.5 might be different than the entire line, right. So you have these parameters R, L and C which are like distributed over the entire line. So in this thing, so we start with what is a simpler version of these models called the L model, right. So this is called the L model of the line. Okay, so if I take a small element starting from Z to Z plus delta Z, which means that this entire thing is of length delta Z. Okay, so if R, L, C and G are measured per unit length in a little element of the transmission line. So this is my entire transmission line starting from 0 to L. I am just interested in a little element here, delta Z, and this little element in this length delta Z looks like this L model. Okay, so what will be the R for this element delta Z? It will be R times delta Z. Similarly with L, G the conductance and C the capacitance, right. Okay, what do I know about these things? I already know the circuit laws, right. So if I apply KVL to the outer loop, so here at Z I denote my voltage as V Z comma T, the voltage at Z plus delta Z as V Z plus delta Z comma T. So that I have to do this because if I say I have a generator here which is a typical setting going to some load here, so the voltage at length 0 at any time t will definitely be different than voltage at length L at the same time instant t, essentially because there might be drop in the line, right. So, the line has its own resistances. So, the voltage here might be different than voltage here, then here, ultimately until it reaches the load. And there are several methods of how to make this drop to be lesser and so on. That is a part of a power system course if you are an electrical engineer and if you have done that course. If you have not done, it does not really matter because we will not really analyze power systems here. Okay. So, if I apply the basic voltage laws V equal to, so if I call this current through this branch as I z, so I just have this simple equation here, right, that V z t is R for the little element delta z, the current times L di by dt, right. So, the voltage here from here till here is the voltage across R, L and the voltage here, which is what? Which is simply V z plus delta z comma t. Again, the time is fixed here, right. So, I am just looking at how the things vary with space. So far we were interested in say d x dot, dx by dt is ax plus bu. So, there is another dimension here in terms of the space. Okay, so I just rearrange terms and write my equations like this, right. And if I will take the limit as delta z tends to 0, this looks familiar to what I learn in calculus as definitions of derivatives, right. Now, for a small element, so this turns out to be the derivative or the partial derivative with respect to z is okay. On the right hand side I have things like this. Okay. So, this is the first equation which starts from a lumped model of length delta z, to which I write down the equations for the entire line. It would seem something like this. So, this is valid for all z between 0 and L. Okay. And these are essentially systems which are now governed by partial differential equations, also called PDEs. Right. Infinite dimensional systems are the systems governed by partial differential equations. Another class of infinite dimensional systems could just be like time delay systems. One way to look at things here would be that if I send a voltage here at time t equal to 0, it might just reach the load which is at length L with some delay tau, right. So, transmission lines can also in some cases be modeled as pure time delay systems, right. So, there is possibly no loss, maybe in some ideal case, just that there is a time difference by the time I transmit my voltage from z equal to 0 till z equal to L. Again, there is a lot of literature on that. So, the reason of also doing this is doing this model explicitly is that the same system can be represented by different models is what we claimed in one of our earlier lectures, and this is one indication or one example of that. Okay, so how do I write the second equation? So, if I look at if I apply KCL to this node here, so I have I z coming from here, I have the delta I here, and I have I z plus delta z, again all at the same time t. So, I just apply the current laws. Okay. So, I just write down I t comma z is delta I plus I z plus delta z comma t, and I just write down this delta I in terms of V z plus delta z comma t and these two elements here, okay, because the potential at this point or the voltage at this point is just V z plus delta z comma t. Okay, so and then I just rearrange terms, take the limit as z delta z goes to 0, and then I have another partial differential equation here, right. Okay, so so these two equations together constitute what are also called the telegrapher's equations or the equations, wave equations for a transmission line. And these are also similar if you come from the mechanical domain of a vibrating string. There is nothing. So, there is a travelling wave there is a travelling wave also here. The structure almost looks similar, and both come from set of conservation laws, right. So, what I said here is like we are essentially looking at systems of conservation laws. Okay, what are the things or what are the physical quantities that are conserved here? Okay. So, let me just take this equation for a while. For simplicity, let me assume G is equal to 0. Okay, what I would have, and let me write down I and V in more of the fundamental terms, right? This is called the charge and the flux. Okay. So, we know that Q dot is I, phi dot is V, and after all the necessary things have been taken care of, I can write this also as dq by dz is, or the partial of q, which again depending on z comma t, till d phi by okay. Now, if I integrate this over the spatial domain, what I have is from say 0 to L, say again dz, and this would be okay. This will have a 1 over c, right. So, this guy goes here. Okay. So, times 1 over c. So, the rate of the flux, or the rate of the flux around the entire, or in the entire spatial domain would just be, so this has dimensions of say q over c from 0 to L with a minus sign. So, this this has just the dimensions of voltage. This is V at 0 minus V at L. Okay. So, whatever is the rate of change in the spatial domain is just what is being exchanged through the boundary. Okay. Similarly, I can write also for the other equation, right, over here. So, if I again write it in terms of q and phi, assume r equal to 0, what I will have is d phi by dz, where phi is the flux, say 1 over L is dq by dt. And similarly to what I had here, I can derive the conservation law. So, if I integrate from 0 to L, dq by dt, dz is then from 0 to L. So, this will be the rate of current, or the rate of the charge, or the increase or decrease of charge in the spatial domain will just be what is being exchanged through the boundary. So, this will be phi over L with a negative sign from 0 to L. This would be phi over L at z equal to 0, phi over L at z capital L at z equal to L. Okay. So, the conservation law. So, whatever is happening in the spatial domain is what is being exchanged through the boundary. I can still write same expression for the energy conservation, at the rate of change of energy in the spatial domain, which is from between 0 to L, is just what is being exchanged through the boundary. Okay. So, keeping this in mind, can I derive expressions or equations which say for example model a traffic flow, right. So, this comes picture from one of busiest highway in the US. So, I will just look at these as one dimensional flow, right. So, because everybody there follows lanes, so I can just say model through one lane, and then it's just like one dimensional traffic flow, right. You don't really go like zigzag as we do in an Indian condition in a laneless situations. Okay, how do I model this, right? So, for example, if I say what does it mean by even modeling this? So, can I have an expression that relates the flow of the cars through a spatial domain or through the entire length of the highway? Okay, this will be clear a little slowly, right? So, let me take a stretch of the lane, right, and denote these points as A to B. Okay. At any time instant t, let n denote the number of cars in this interval from A to B at time t, right. So, this is the number of cars which are here, say there are like maybe 1, 2, 3, 4, 5 cars. Okay. Now, what happens from t to delta t? Well, it is a moving traffic, so the number of cars could possibly have changed, right. So, the change in number of cars in a small interval delta t is what? It's just a difference, right. So, I look at the number of cars in the interval a b at the time t plus delta t minus the number of cars in the interval a b at time t. So, I am just writing down the change in the number of cars in a small interval delta t. So, I am just interested in this interval a to b, how does the number of cars change from t to delta t. Okay. Now, if say the traffic is just still, right, it is not moving, what will be the change? The change will be 0, right, because no cars enter and no cars leave. On the other hand, if say the traffic is moving in a very steady state, right, say it is like okay, one car enters from here and one car leaves from here, still the number of cars would be just 5, for example, in this case, right. So, one is entering, other is leaving. So, the change from t to t plus delta t will again be 0. So, the change is caused in this the change will be caused only when there is a difference of cars flowing into the interval at x equal to a and leaving at x equal to b. Say there are 2 cars leaving this entering a and say 4 cars leaving b, then there is a change, right, kind of obvious. Okay. So, now if I am just standing at this point, say at a, and if say someone else is standing at this point b, I can measure the number of cars passing this point a, for example, at time t, and I call it the flux q x comma t. I can do it for point b, I can do it for any point between a and b, let us just generally call it x, right. So, the number of cars passing the point x at time t. Okay. Now, so the change, as I said, is caused only by difference of what happens at point a and point b. Okay. Now, the change in total number of cars in this interval will just be given by this one, assuming that cars leaving are treated as negative at point b and then cars entering are treated as positive, right, in the interval delta t. Okay. Now, this change is equal to this change, because here I am just counting what is happening between points a and b, and I know that the change that happens between points a and b is only governed by what happens at x equal to a and x equal to b. Okay. That I quantify as this number. So, this 1 is equal to this 2, right. So, that is what I write here. Okay. Now, I divide by delta t here and then take the limit, and I have a nice looking ordinary differential equations in terms of n, that the rate of change of number of cars in the interval a comma b is just defined by what is the number of cars that are leaving point b and the number of cars that are entering point a. So, what I have done is I have just written down a model for this statement here. The change can only be caused by a difference of cars flowing into the interval at x equal to a and leaving at x equal to b, right. So, if these two are equal, then this is 0, d by dt, if this and this are equal, then d over dt of n is 0. So, I just have a nice looking model for this statement. This statement I know is always true, right, it is just basic observation. And this relation holds for any point, just say if this is like starting from length 0 to 100 kilometers, it holds for maybe a b here, or any interval. So, okay, I am not really interested now in defining this interval. Can I just write a general expression, right, for any point, right? Okay. To do this, I define another quantity, which again is kind of obvious, right? There is nothing really to be surprised about this. So, given a scenario like this, right, I can like this, I can always define the car density, the number of cars per unit length at position x and time t. Physics teaches us about density, and what I know about density, or from what I know from physics would be that, well, there will be, I cannot have infinite amount of cars per unit length, right. So, the density is upper bounded, I can only hold maybe 4 cars per meter or per 5 meters or something. Okay. Now, if I define density, I can then write down the number of cars in the interval a b at time t simply as a function of density. Right. This is again from physics. Okay. So, now I can relate these two expressions also now to the density. Okay. So, this so what do I eliminate here, right. So, this a comma b here is actually can be written more generally here, right, and this a comma b can be arbitrary anything now. Okay. So, this the rate of change of cars in the interval a b at time t is just can be rewritten in terms of the density. Okay. This also, well, then this is also related to this. Okay, that is what the next expression says, that minus q b comma t plus q a comma t is just now written. Okay. This I can write, so assuming that this q is differentiable, this q is differentiable with respect to x, I can write minus q b comma t plus q a comma t as this expression, and now I just combine these two. Okay, these two via this expression, and I get something like this, right, from the integral a to b d rho by dt plus dq by dx times dx equal to 0, right, assuming smoothness and all that nice properties. Okay, this is what I call as the global conservation law, right, that the number of cars are conserved, that whatever is going from point A is actually coming out at point B, and that there is no all of a sudden a car does not disappear or appear from nowhere. A little proof will also show, okay, we will skip the proof, that I can just write this down as a local conservation law just for any point x, and this point is valid for any say any point between say 0 and L, if L is the length of the entire highway. Okay. So, this also resembles the mass conservation law in fluid dynamics. Okay. What is the relation, right? So, if I look at, so what I do here is I just look at cars as really small infinitesimal points moving through a straight line. Okay, that is essentially how I model fluid also, like very small particles moving in a straight line, and it is just a one dimensional motion, it just goes x, it does not, I am not really worried about this direction or this direction at the moment. Okay. So, even though, well, physics or the fluid dynamics is complete by another conservation law called also the momentum conservation. Okay. Again, we will not go into the details of these things. So, just to show you an illustration of how starting from a physical observation of traffic flow, we can actually write them down as partial differential equations. Okay. Of course, the aim of the course will not be to look at solutions of these equations, which will depend on initial plus boundary conditions and so on, but just to give you an idea of how to start from basic physical observations to arrive at mathematical expressions. Of course, these are very simple models, then you can derive more complicated models on is the flux depending on the density, is the flux depending on the velocity of the car, upper bound on the velocity, and there are okay more things on that. So, for those details I can just refer you to these notes which are available online. Okay, we pause here before we go to the next set of examples, which will be on computing systems.